Hey everyone and welcome. Today we are going to tackle a topic that you see absolutely everywhere in science and engineering, second-order differential equations. Now, I know they can look pretty intimidating, but what if I told you there's a simple algebra trick to solve a huge class of them? Let's get into it.
Okay, so first, let's set the scene. We're going to focus on a very specific, but, an incredibly common type of differential equation. This is the kind you're going to see over and over again in physics, chemistry, you name it.
All right, this is the beast we're trying to tame. It's a second-order, linear, homogeneous differential equation with constant coefficients. Yeah, that is a mouthful, I know. But all it really means is we've got a second derivative, y double prime, the coefficients a, b, and c are just plain old numbers, and the whole thing is set to 0. So the million-dollar question is, what function y can possibly make this equation true?
Now you're probably thinking, oh man, here comes some super advanced calculus technique, right? But the real breakthrough, believe it or not, comes from a guess that's almost like magic.
Here it is. This is the magic. We just guessed that the solution looks something like the exponential function e to the power of r times t. So, why this function? Well, the beautiful thing about e to the rt is that its derivatives are just multiples of itself. And that is the secret sauce that lets everything in our equation hopefully cancel out and equal 0.
So let's actually do it. Let's plug it in. If y is e to the rt, then its derivative y prime is r times e to the rt, and the second derivative y double prime is r squared times e to the rt. When you substitute those in, you get this. And look at that. See that? Every single term has an e to the rt in it. That's no accident.
And since that e to the r term is in every part, we can just factor it out. Now, this leads to a really crucial moment of insight. The exponential function, e to the rt, can never, ever, ever equal 0. So for this whole thing to equal 0, the other part, the part in the parentheses, that has to be 0.
And boom, just like that, we've turned a scary calculus problem with derivatives into a simple algebra problem. It's just a quadratic equation. You've been solving these for years, right? This little gem is called the characteristic equation. So the whole point is, find the r's that solve this, and you found the key to your differential equation.
This awesome insight gives us a rock-solid, 3-step recipe that's going to work every single time for this type of problem. Let's break it down.
Okay, step 1. Just write down the characteristic equation. You literally swap y double time for r squared, y prime for r, and y for a 1. Step 2, find the roots of that quadratic. We'll call them r1 and r2. And step 3, you just plug those roots right into this general solution formula. The c1 and c2, they're just constants for now. It really is that simple.
All right, theory is great and all, but let's get our hands dirty and make this real with a couple of examples. Let's see this recipe in action.
Okay, first up, u double prime minus y prime minus 12y equals 0. This is a classic example. Let's fire up our recipe.
All right, step 1. Write the characteristic equation. That's just r squared minus r minus 12 equals 0. Easy. Step 2, we factor that, which gives us roots of 4 and negative 3. And step 3, we just plug those right into our general solution formula. And just like that, we're done.
So that was the general solution, but what if we have a bit more information? In a lot of real-world problems, we actually know what the system was doing right at the beginning. We call these initial conditions, and they let us find a very specific solution.
Let's try this one. Solve y double prime minus 4y equals 0. But this time, we're also told that at time 0, the function's value is 1 and its slope is 2. Okay, so the characteristic equation is r squared minus 4 equals 0, which means the roots are 2 and negative 2. That gives us our general solution, y equals c1 times e to the 2t plus c2 times e to the minus 2t. Now we just have to use those initial conditions to figure out c1 and c2.
Okay, listen up because this is super, super important. This is a spot where a lot of people make a mistake. For that first condition, y of 0 equals 1, we use the general solution directly. But for the second condition, the one involving y prime, we first have to take the derivative of our general solution. You gotta do it. Don't forget that step.
So when we plug in t equals 0 into both our solution and its derivative, we get this beautiful, simple system of two linear equations. The first condition gives us c1 plus c2 equals 1. The second one gives us 2c1 minus 2c2 equals 2, which, just simplifies down to c1 minus c2 equals 1. Look at that. The calculus problem has completely melted away into high school algebra.
And hey, solving this system is a piece of cake. If you just add the two equations, the C2's cancel out, and you get 2 times C1 equals 2, so C1 has to be 1. And that means C2 must be 0. We plug these specific constants back in, and we get our final unique answer, y of t equals e to the 2t.
So we can find the solution, that's great, but what are these roots, these R values? What do they actually mean? Well, it turns out they tell a story about how the system behaves over time.
Just think about it. If you have e to a positive number times t, that term is going to grow exponentially forever as time goes on. It's going to explode. That's like population growth or compound interest. But if r is negative, e to a negative number times t is going to shrink, getting closer and closer to 0. That represents decay, like a vibrating spring slowing down because of friction or a hot object cooling off. The signs of the roots literally tell you the long-term fate of your system.
So there you have it, a really powerful algebra trick that lets us solve a huge class of differential equations. But what happens when the roots of our characteristic equation aren't two different real numbers? What if they're repeated? Or what if they're complex? Well, that's when things get really interesting. That's when we start to see things like oscillations and damping come into play. But that's a story for another time.